You ever see a study or a news report flash some fancy statistical analysis on screen, and you just kind of nod along wondering what on earth it actually means? Well, today we're going to pull back the curtain on one of the most common tools out there, regression analysis. We're going to learn how to read the lines.
So you might see something that looks a little like this. This is a real regression equation straight from our source material. It's built to model the relationship between a person's height and their weight.
Okay, but what's the deal with this string of numbers? I mean, it looks like a math problem, sure, but each one of those numbers is telling a very specific story about the data it came from.
And that gets us to the really big question, right? Just because a computer spit out an equation, does that automatically make it true? Or useful? That's what we're here to figure out. We're going to give you the tools to look at these lines and decide for yourself.
So let's start at square one. At its core, what is a regression anyway? What are we even looking at? Well, imagine you've got a graph with a whole bunch of dots scattered all over it. That's your data. All regression analysis is really trying to do is find the one single straight line that cuts through that cloud of dots in the best way possible. It's all about finding that pattern hiding in the noise. And that line? That's a regression line. It's our best guess, our model of the relationship. Now, it almost never passes through every single point, and that's okay. Its job is to show the average trend, the general vibe of how one thing changes when the other one does.
All right, so how do we actually build that line? Well, every regression line has a blueprint, and that blueprint is its equation. This is what tells us exactly where the line goes and, more importantly, what it all means.
Any simple straight line really only has two main parts. First up, you've got the slope. You can think of that as the steepness. It answers the question, for every one step I take to the right, how many steps do I go up or down? And second, there's the y-intercept. That's just the starting point, where our line officially crosses that vertical axis.
Now, the slope is usually the star of the show because it's so practical. Our source material from Minitab gives a perfect example. Let's say we're predicting test scores based on training time. If our slope is 4.3, that means for every single extra hour of training, we expect, on average, a 4.3-point jump in the test score. See? It's a direct, concrete number. Okay, so the slope makes sense. The intercept should be just as easy, right? Well, here's where it gets interesting. According to statistician Jim Frost, that other number, the y-intercept, it's almost always totally meaningless in the real world. Wait a minute. If it's meaningless, why is it in basically every single regression equation we see? Why do we even bother with it? Because it has a crucial job to do behind the scenes. The intercept isn't for us to interpret. It's there to anchor the line. It moves the entire line up or down so that, on average, our predictions aren't consistently too high or too low. It's a thing that makes sure all our misses, all our errors, cancel each other out perfectly. It keeps the model honest. Okay, so we've got our line. We understand its parts. But is it any good? How do we know if our model is an A+ student or if it's barely passing? How do we grade this thing? Well, one of the first grades you'll see is the p-value. Think of this as a fluke detector. A really small p-value, usually anything less than 0.05, is basically the model telling us, hey, the relationship I found here is probably not just some random coincidence. It's a good sign that our variable is actually doing some meaningful work. And then you've got the big, flashy number everyone loves to talk about, r-squared. This tells you what percentage of the up and down movement in your outcome variable can be explained by your model. So in one of the examples from our sources, an r-squared of 76.1% means the model can account for over 3/4 of the variation in people's body fat. Sounds pretty good, right? But hold on. A percentage is kind of abstract. It doesn't really tell you how close your predictions are in the real world. I mean, is explaining 76% good enough? To know that, we need to know what our margin of error looks like. And for that, we need to look at r-squared's less famous but way more practical cousin, s, the standard error of the regression. Well, r-squared is a percent, s is measured in the actual units you care about. It tells you the typical distance between the real data points in your prediction line. So if s is 3.5% for that body fat model, it means our average guess is off by about 3.5 percentage points. That's a number you can actually sink your teeth into. So far, we've been living in a nice, clean world of straight lines. But let's be honest, the real world is almost never that simple. Things get complicated. So what happens then? I mean, think about it. Is there one single best way to manage a team? Nope.
Is one diet always the best? Of course not. The answer to most interesting questions is almost always, it depends. And in statistics, we can actually model that. It's called an interaction effect. Our source material from McGuinness uses a great example, leadership. A very direct, top-down leadership style might be exactly what you need in a crisis. But for a creative project, it would probably be a disaster. The situation changes the effect of the leadership style. Capturing these "it depends" moments is how we build models that actually reflect reality.
The other way reality gets messy is, well, with messy data. What happens when you have those weird data points, the outliers, that just don't seem to fit the pattern at all.
Now check out this table from the OTS Canadian Journal. This is fascinating. Look at the top two rows. That's the standard, run-of-the-mill regression. When you throw in some contaminated data, some outliers, the numbers barely move. Now, that looks stable, but it's actually really bad. It means the line is being subtly pulled off course. But now look at the robust model, Ransack. It sees that outlier and says, whoa, that's noise, and it dramatically changes its line to ignore it and stick to the real pattern. And that's the key difference. A standard regression is kind of gullible. It can get fooled by those outliers and give you a false sense of confidence. A robust model, on the other hand, is built to be skeptical. It actively redraws the line to protect the result from being skewed by that noise. And that really brings us to the whole point of all this. A regression line is an amazing tool, but it's also a massive simplification. Your data is always telling a much richer, more complicated story. So the question you always have to ask yourself is, are you listening to the whole story, the curves, the context, the outliers, or are you just listening to the parts that happen to fit neatly on a straight line?